Hey YouTube, what's going on? Daniel Dallas here. Alright, we just gonna go to linear programming. So that specific video dedicated to NCERT Mathematics Class 12. So it's dedicated to newcomers, guys. Hello and welcome. Join us. Actually, really appreciate your comments and actually give you feedback as a new video dedicated to computer linear programming problems. All right. So, and for GCSE students, it will be a particular interest as well because you guys might use that as an extension for your GCSE internal projects. So this is going to be a real basis and you can use that to maybe arrange your project in a proper and interesting way. So trust me, this is very interesting information, so you might have a look as well. All right, so what I'm going to discuss here. Before, in the previous video dedicated to general idea how to optimize the objective function z, and that was linear function. Z was set up as x plus b, y, where a and b is simply coefficients, some numbers, and x and y are decision variables. All right, so here I'm going to discuss the corner point method, and I'm going to go through the steps that you need to follow in order to successfully solve any linear programming problem. And actually, this is the manual ready to use in order to have success in solving this sort of problems. Okay, so I'm just go through the steps quickly. The method should comprise the following steps. The first, you need to find the feasible region. Hope you guys remember that feasible region is basically the region that represented by set of inequalities, and actually a set of inequalities defines this region. Okay. And here, as the result of the first step, you need to determine vertices, or basically corner points. So if you which way you can do that, just remember we need to set up the lines, because all inequalities are linear, so the graphs of those inequalities become lines, right, straight lines. So you can set up all those boundaries and see what sort of region you've got. So that's why it should be a convex polygon in ideal case, but I'll give you examples probably in next video. What if it's open? It means that the region is not enclosed completely. Okay, so somehow you found vertices. For those who are not sure how to do that, just watch the previous video. I did it in this video. I'll also show, but real quick. So the second step, you need to evaluate the objective function z, x plus by. So this is general case, but for a given problem, you'll be given this function as some linear, let's say 2x plus 3y, for example. And you need to evaluate z value and each vertex point. So basically, once you set up your region, you've got vertices, let's say v1, v2, v3, and v4 with coordinates, and you need to calculate values by plugging the coordinates x and y into z functions. Okay, so if you define like m, or max and mean stays for the largest, the maximum, and the smallest values of those points, so we can go to step 3, because right now we are going to define what sort of region we have. If region is a convex and it's bounded, according to the theorems that we briefly discussed before, if region R is bounded, so your max and min values are basically maximum and minimum values of z. So if you have, let's say, quadrilateral, you calculated z values in each vertex point, so you basically know the values for z. So you set up the set for z1, z2, z3, and z4, for example, for if you have a region consisting of 4 vertices. So in this case, you can visualize all the values, and if the region is bounded and represented by convex polygon. So maximum and minimum values becomes the max and mean values for z. Okay, so let's say you defined this is max, and for example this is mean. So in this case you already solve the problem, and you can figure out z1 and z4, for example, as maximum and minimum values. So they are optimal values. But in the case that if the feasible region is unbounded, okay, so I mean it will have some open half of the plane, for example. So you need to test, actually, now you need to test. You calculated, so let's say max, and max is going to be the maximum value of z if the open half plane determined by inequality x plus by, that's your z actually, more than max, has no common points with the feasible region. So what it means? It means that if you have region R with open half and you calculated z, that's going to be the maximum value. So if you construct inequality and you have your z function more than max value, and this like open half plane, because inequality actually indicates the boundary, right, and the open part of the plane actually. So, and if it has no common points with the feasible region, in this case max becomes the maximum value of z. Otherwise z has no maximum value. So if this region will have, let's say you set up z, right, and if opens, so that's your actually z, and z more than max is this part of the graph, or sorry, not the graph, but this part of Cartesian plane. And as you can see here, they have this part with the region R, they have common points. In this case, the max value that you calculated at the vertex points is not actually the maximum value for z. But if it doesn't have any common point, probably except for the only one point that you have on the boundary and at the vertex point, so in this case max become the maximum point. Okay, so maybe on words is maybe pretty complicated, because actually it's better to go through example and you understand, but this is the rule, so that's, you need to follow that step. When you actually see the example, it will be much easier for you. The same you test for minimum. So if mean that you actually calculated, let's say z4, is the minimum value of z, so only in the case if open half plane determined by another inequality, in this case z is less, basically z is less than the value that you calculated on previous step 2, actually it has no points in common with the feasible region. Okay, so in this case you have mean as minimum value. So otherwise, let's say this is the region, and let's say your z equals mean, a straight line, and that part indicates this inequality, and if they have common points with the region, so in this case this mean is not the minimum value, so that's why z has no minimum value. Okay, it's better to see on the example, and here what I've got. So that's NCERT problem chapter 12 actually, if you have the reference to your book, guys. But I decided to set up my own example. So here we have the problem, so you need to minimize and maximize the following objective function with the equation z equals 3x plus 6y, and it's subject to constraints. So those constraints you can see here. Actually, okay. Yeah, it's impossible to do. All right, so anyway, so you have constraints set up by set of inequalities. So what we're going to do right now, we're just going to do according to the steps. The first one, you need to find the feasible region. Basically, you need to, by drawing graphs of each inequalities, you need to set up them on Cartesian plane, and hence you will define the region. Okay, so let's do it right now. I'm not gonna be long-wise here, so because actually I'm going to save my time, so hope you understand how to build this. So I'm going to be quick. So y, x, z, and the first x more equal than 0. This is the vertical line, so that's the first one, and that's basically y-axis. And if you set up that one, let's say with that color, it's going to be your first boundary. Okay, let's set up like this. So the next about y more, and actually the right hand side, because x more equal than 0, the right hand side is going to be your visible region for that inequality. So let's go to the second one, y more equal than 0. That's definitely horizontal line with an equation y equals to 0. So that's the second part. So first one, second one, and actually you've got the first quadrant here if you combine 1 and 2. So the next one, x less or equal than y, but actually you need to consider from y side, so y more or equal than x. So if you set up the line 3 with the equation y equals x, you'll get the identity line. So identity line is the line that goes as a bisector of 90 degrees angle. So it means it's going to be here. So an equation for that, this is 3, and equation for that y equals x. But right now, be careful, you need to estimate from y side, so y more equal than x. So actually the top half, right? The top half. So actually here, this top open triangle is going to be a visible region for us if you combine 1, 2, and 3. So let's go to 4. Here we've got x plus y equals to 8. So that's the line 4. Actually, I indicate this the line 4. So it will have 8 as y-intercept, because 8 is going to be y-intercept. So 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be here. All right. So I put 8 here. Okay. This is one point. And the second point, when let's say y equals 0, you'll get x equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's also an identity line, but it goes with negative gradients. So if you connect that, it should go also through the nodes of your grid lines. So to be precisely, it's going to be like this. So x plus y equals to 8. And now if you estimate from y side, again, you transfer, imagine that you transfer x to the right side of inequality, you've got y more equal. So actually, in this case, we are going to have the top part, right, of the graph. So right now, let's see, yeah, we've got that triangle right now. Yeah, perfect. And now what I'm going to do, I'm going, I guess, to shift a little bit down, because right now it seems to me that I won't have enough space. Okay, so yeah, it actually, for some reason, it combined everything here. Okay, so anyway, I'll try to put that down a little bit. Sorry for that inconvenience. Okay, so I guess that's okay. So maybe let's try to do this way. I don't know. Doesn't work. Yeah. Anyway. So we've got we've got this. So our constraints actually now it's a really bad. Okay, I just better if I turn it back. So yeah, I'm not gonna have any experiments from that. So that's, you see, sometimes software is a little bit buggy and you actually are releasing that, but it's not so reliable. Okay, so next one. So x plus 2y equals to 21. That's line 5. And what I'm gonna do right now, I'm gonna set up the line x plus 2y. So for that reason, I just create the table values. So I need to have 2 points for that. So the first, as I can see, that's negative gradient, yes, negative 1 over 2, I guess, and 21 by 2, 10.5. So when x is 0, actually I've got 10.5, that's y-intercept. 10.5 is going to be somewhere here on the very top. So what I'm going to do right now, I just want to down a little bit because I really don't have enough space. So I down everything. Okay, perfect. So right now what I'm going to do, I just going to increase my, so basically prolong my x equals 0 line, and now I'm going to set up 10.5. So because this is the level of 8, it's going to be 9, it's going to be 10, so 10.5 is that point, and this is y-intercept for line 5. Okay, I've got 1 point, and what I'm going to do right now, because the line will go with negative gradient, so you can actually rearrange that equation into the gradient intercept form, and you'll get negative x over 2 plus 10.5. So in this case, what I'm going to do, I just simply want to detect another point, and because it goes that way, so actually I've already got the region, so it's somewhere here, because y is going to be lower than that of the line, so than that boundary. So I'm going to look for y-intercept. I've already got, but I'm going to have intersection with the line 3, so with that line, and I'm going to determine this point. So what I'm going to do, because anyway I'll need this as well as that corner point according to our method. So right now what I'm going to do, I'm just going to solve x equals y with the fifth equation, x plus 2y equals 21. So I'm just going to solve that simultaneously, and x equals y. So if I plug that, x equals y, if I plug that, I'll get basically 3x equals 21. So from where, if I combine them, x is going to be 7. Okay, so when x is 7, because x equals y, so I've got also 7, and I have points of intersection, 2 lines, lines 3 and lines 5. Okay, so let's do that. 1, 2, 3. So that's definitely point 4 and 4. I'm not gonna do that. So actually I used determining on the step 2 I used, on the step 1 I used the method by inspection, because I clearly see that this line is an identity line, so I can easily define 4 and 4 coordinates and that point of intersections of 2 lines. So right now this is line 4, by the way, and the line 5 should go through the point 7, 7, okay, 5, 6, 7 is here, and 7 is also here. So that's another vertex point. So right now I'm going to connect with the last line, which is in this case line 5, with an equation x plus 2y equals to 21. Okay, so now I've got everything. Now I've got everything in order to start doing calculations. So where's my region? So my region is here. Okay, so maybe, oh no, sorry, it doesn't work for some reason. No way. Okay, so we have NCERT problem chapter 12 exactly in the region. Anyway, so right now what I'm gonna do, I've got a vertex point here, 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 and here. And I've got all the coordinates. So what I'm gonna do, on step 2, because right now we actually got step 3 and the region is bounded, so we need actually to find the minimum and maximum value for z in this case. So actually we are trying to execute step 2, and here what we're gonna do, we just put the coordinates for each vertex point. So for here, so here is gonna be 7, 7. We also want to say that this is 0 and 10.5. And the last one, it's here with coordinates 0, 8. Okay, we've got 4 vertices. I can mark them as using the letters. Let's say A, B, and C. That's okay. A, B, C, and the last one D. So we have region as the quadrilateral, so it's here. That's our region. So one more time, you can check by inspection for your inequalities. So that's region is going to be there. And as you can see, it's convex polygon, so it's bounded. Okay, but the main purpose of demonstrating this example is actually to show you one detail that actually I can see there. Okay, so let's go and just try to calculate z values. So we are going to create the list of z by plugging the points. So actually, if I plug 0 and 10.5 into z value, let's see what I've got. So I've got 63, I guess, yeah, 0. So I'm going to use my z function as an objective one. So one more time, and just duplicate that. Z equals 3x plus 6y here. And if I plug 10.5 and 0, I'll get 63. Okay. So next one, if I plug that coordinates, so for z, 7, 7, I'll get 21, and actually in total, I've got 63 here. Oh, you see that z function and alone, basically in 2 vertices, will get the same value. Okay, looks like it's maximum value, but anyway, so let's plug point D 0, 8, and from where we can get a value, if we plug 0, 8, we've got 8 times basically 6, it's going to be 48. Yeah. So, and the last one, 4 and 4, if we plug that, we'll get 36. Okay, so now I just highlight them. Okay, so here, 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 and the last one is here. So we've got 3 values for z, and definitely 63 is going to be the maximum value, so I can write that max z equals to 63, and it occurs at two vertex points. So vertex C here and vertex B. So we've got at C and B. So what it means, if maximum value occurs at two vertices, according to the theorem, it means that along this segment, so right now I'm going to use the green color. So along this segment from C to B, Z value is going to be the same, and the value for that is going to be 63. Okay, so it means no matter which coordinates you plug, so you can plug this point, you can plug this point, no matter which point you take on that segment, you will have the value always to be 63. Okay guys, what's the clue? How to probably test yourself, for example, on before like doing any calculations, how try to understand that you'll have this case, exactly this case. Let's have a look at our z function. So z function is simply 3x plus 6y. Let's have a look at the segment that we actually recently tested, CB. So if you write the equation for the segment CB, it will have, this is the line 5, it's here, it will have an equation like x plus 2y equals to 21. And look guys, 3x plus 6y, if you multiply equation for the segment by 3, you actually will get 3x plus 6y here. So what it means? It means that two functions, they are linear dependent from each other. So that means they represent the same lines. If you multiply value by 3, and you can do anything with general equation, you'll get 3x plus 6y. On the right side, if you multiply by 3, instead of 21, you'll get 63. And that's the maximum value for your function. So before doing that, before like trying to solve, have a look at your z function, okay? And have a look at any segment. Maybe any, inequality here that actually can be turned into the equation of the line. So here, if you compare with 5, x plus 2y equals 21. If you multiply by 3, everything, you'll get your z function, 3x plus 6y, which will be equal to 3 times 21, 63. And you already know the optimal value. So it doesn't give you any guarantee whether it's maximum or minimum, but in this case, you definitely know that your one of the optimal value might be minimum and might be maximum, actually lays on the line x plus 2y equals 21. That we actually found, and that how we proved by our observations. Okay, in this case. So what about the minimum value? The minimum value is 36, and that's okay. So it's going to be the minimum value for our function that can be reached at the point A. So max is 63, and mean value, mean z, is actually 36. Okay guys, hope you like that. Don't forget to subscribe, so share your comments. I really appreciate that you actually had dialogue with me. So for GCSE students is also, I think it's a very interesting topic that can be a basis for your guys' projects that you're doing within schools. So actually within the school, within classes. So actually if you're set up some real life problem and try to figure out using that approach, using theorems, so provide some theoretical basis, so your work will be, I think, assessed as A star. So if you can do that, so probably the appropriate tool that where you can do such modeling is Microsoft Excel. So you can program cells. It takes about like 5-10 minutes to do that. And actually, if you draw that region using appropriate charts, So the project will be already done on 50%. So on top of that, you just put some text descriptions, and that's how your project can be completed. Okay, thank you. That was Daniel Dallas, and see you later.